To all my viewers, here is a nice piece of advice for your well being. A river doesn't fight obstacles, it flows around them. A lion doesn't respond to the barking dogs, it moves forward. A mountain doesn't shake because the wind howls, it stands firm. In the same way, don't be disturbed by those who seek you to pull into their storms. Stay still and stay silent. Your growth will be your answer and your peace will be your response. And let's move on to today's video on group theory. So here is the most important problem. So what is the problem here? Show that the set of nth roots of unity form a finite abelian group with respect to multiplication. So we have to find the algebraic structure. What is the set here? The set is nothing but the set of all nth roots of unity. See here, we have to show that it is an abelian group. In order to show it's an abelian group, we have 5 properties here. One is closure, associativity, identity, inverse, and commutative law. So if all the 5 properties holds, we say that that group is a commutative group or an abelian group. So here, what is the binary operator? Multiplication is the binary operator. So first we have to understand the problem, and next we have to frame the structure, that is algebraic structure. So what is nth root of unity? So here consider, so 1 power 1 by n. 1 power 1 by n can be written as 1 plus I into 0 power 1 by n. See here, 1 can be written as cos 2 pi k plus I sine 2 pi k power, this is 1 by n. See here, this is 1 by n. So here if you observe this one, so if you keep k value as 1, 2, 3, 4, anything, so that will be the even pi value is equal to 1. And here if you keep the k value as 0, 1, 2, 3, 4, anything, it will be 0. So in place of 1, I have written cos 2 pi k, and in place of 0, I have written sine 2 pi k per 1 by n. According to the De Moivre's theorem, so this 1 by n is written as, that is 2 pi n k plus this is I sine, this is 2 pi n k. See, clear? And according to the Euler's theorem, so this can be written as cos theta plus I sine theta can be written as e power I. This is 2 pi n k, where k value runs from, this is 0, 1, 2 and so on n minus 1. So this is nothing but the nth root of unity. See here, nth root of unity. If you keep any power as n, so that it should get a unity. If you shift this 1 by n to that side, see here, if you shift 1 by n to that side, so this will be unity as an answer. And now I am framing a set here. Now set the set of nth roots of unity is, see here, so G is a set such that it is of the form e power, this is I 2 pi n into k, where, see here, 0 less than or equal to k less than or equal to n minus 1. So what is the binary operator here? Multiplication is the binary operator. We have to use multiplication as a binary operator, and we have to show all the 5 properties. One is closure, associativity, identity and inverse. So here let me write the set here. G is a set, so which is of the form e power I 2 pi k by n, where 0 less than or equal to k less than or equal to, this is n minus 1. The first property which I am going to show is the closure property. See here, for closure law, we have to take 2 elements. So for closure law, I am taking the 2 elements. Let a comma b belongs to G. So I am taking 2 elements, that is, let a comma b belongs to G. So here a value is nothing but e power I 2 pi r by n, where, and b value is equal to e power I 2 pi n by s. Here in both the cases, 0 less than or equal to r less than or equal to n minus 1. Here also 0 less than or equal to s less than or equal to n minus 1. And now we have to multiply these two. So according to the closure property, if A belongs to G, B belongs to G, and this multiplication also should belongs to G. That is e power, this is 2 pi n into R into, this is I, this is 2 pi by n into S. So here if you take common, that is 2 pi by n, so this will be R plus S. See here, R plus S again is a term here, that is 0 less than or equal to, this is R plus less than or equal to, this is 0 less than or equal to R plus less than or equal to. So if you add this one, this will be 2n minus 2. So this will be 2n minus 2, which again belongs to G. So this is of the form e power I 2 pi n into some quantity here, which is again belongs to G. Therefore, we say that A belongs to G, B belongs to G, implies A dot B belongs to G, and therefore I say that G is closed. G is closed under dot. G is closed under multiplication or dot here. So this is the first case. And the next one here, what we have to show? Associative property. So according to the associative property, associative law. So in this associative law, we say that since the nth root of unity, since the nth roots of unity are complex numbers, so these are all the complex numbers, 1 plus I into 0. These are all the complex numbers, and we know that, see here, we know that the set of complex numbers satisfy the set of complex numbers satisfy associative law. Satisfy associative law. Therefore, we say that G is associative. The set G is associative. Clear? It is closure, it is associative. And the next thing what we have to do, so we have to prove for identity law. For identity law, everybody knows that for the multiplication 1 will be the identity law. See here in this, so what is our A here? So A is equal to e power I 2 pi n into some R, where 0 less than or equal to R less than or equal to n minus 1. And now this time I am taking, so this time I am taking 1 as. So if I keep R is equal to 0 here, then R1 value is equal to, see here, e power I 2 pi by n into 0. So this value is 0. So anything to the power of 0 is 1. And now I'll multiply these two. That is A into 1. So A into 1, what is A here? E power I 2 pi n into R. And this value is nothing but e power 2 pi n into 0. So this is 0. So this will be e power I 2 pi n. And this can be written as R plus 0. So which is equal to, this is I power 2 pi by n into R. So clearly this value is A, and therefore we got A dot 1 is equal to A is equal to 1 dot A for every A belongs to G, and therefore 1 is the identity element. Therefore here clearly 1 is the identity element in G. So as you know that for the multiplication, 1 will be the identity element with respect to multiplication, and 0 will be the identity element with respect to the addition. And clearly, see here, and clearly, and the next property is identity. Next one is inverse. Inverse law. Inverse law. So in this case also, let A is equal to, see here, let A is equal to e power, this is I 2 pi by n into R belongs to G, where 0 less than or equal to R less than or equal to n minus 1. So this is of the form e to the power of I 2 pi R by n belongs to G. So which is from the set G, that is set of nth roots of unity. Then there exist A inverse is equal to e power I 2 pi n into, this one is n minus R, which again belongs to G. See, this also belongs to G, such that such that if I consider A into A inverse, so if I consider A into A inverse, what is our A value? That is e power I 2 pi n into r, and this is A inverse is nothing but I, this is 2 pi n into this value is n minus r, and therefore if I take common, that is 2 pi by n common, this will be, see here, r plus this is n minus r. So if I cancel this one, and what remains, e power, that is I 2 pi n into here n. So if I cancel this one, so this will be e power I 2 pi. So according to the Euler theorem, this can be written as, this is cos 2 pi plus this value is I sin 2 pi. Cos even pi is 1 and odd pi is 0. So the value again is equal to 1. So here what I have considered, A into A inverse, and I got as 1. Therefore, A into A inverse is equal to 1 is equal to, this is A inverse into A. Therefore, G has an inverse element. Therefore, G has an inverse element. G has an inverse element. So 1 is the identity element and G has the inverse element. And the next thing what I am going to show here is a commutative law. So according to the commutative law, so for the commutative law, what we have to write? So for the commutative law, the nth root of unity, see here, I am clearly writing that the nth roots of unity are complex numbers. Which numbers they are? Complex numbers. They are complex numbers, and we know that, see here, we know that the set of complex numbers form a commutative law. And therefore, under multiplication, see here, under multiplication, therefore G is commutative. Therefore G is commutative. And all the 5 properties holds, and therefore we say that G is a finite abelian group. So this is a finite abelian group under multiplication. See here, let me explain you for one time. The first thing here is we have to show that nth roots of unity form a finite abelian group with respect to multiplication. See, nth root of unity means, see here, 1 power 1 by n, we consider it, this can be written as 1 plus I into 0. So 1 is nothing but cos 2 pi k, and 0 is nothing but I sin 2 pi k. And if I bring this k inside, so according to the De Moivre's law, so here this can be written as cos of 2 pi n k plus I sin 2 pi n into k. So according to the Euler theorem, this can be written as e power I theta, where k runs from 0 to n minus 1. Now the set of nth roots of unity is this one, and after getting the set, so multiplication is the binary operator, and now we have to show all the 5 properties. The one is the closure law. So I have to take 2 elements from the set G, that is A belongs to G, B belongs to G, and I have multiplied A dot B, and this also belongs to G, and therefore G is closed. According to the associative law, since the nth roots of unity are the complex numbers, we know that the set of the complex numbers satisfies associative law, and G is associative. And the next thing here is identity law. According to the identity law, we know that for the multiplication 1 will be the identity, and therefore 1 can be written as this one. So A into 1 considered, so this is A and this is 1. So if I add this one again, I got 1, and again I got A, and therefore A into 1 is equal to A is equal to 1 into A, and therefore 1 is an identity element, G has an identity element. And according to the inverse law, I have taken A as A from the set G, and therefore I have considered A inverse as this one. If I multiply A into A inverse, I got 1 as an answer, as 1 which is equal to identity element. Therefore A into A inverse is equal to 1 is equal to A inverse into A, and G has an inverse element. And finally we have to show the commutative law. According to the commutative law, the nth roots of unity are the complex numbers, and we know that the set of complex numbers form a commutative law. So A into B is equal to B into A, and under multiplication, therefore G is commutative. G satisfies closure, associativity, identity, inverse, and commutative law, and therefore we say that G is a finite abelian group. This is the most important problem. If you understand, please pass it on to your friends. If you don't connect to this for the first time, please repeat this video for one more time, then it will be very clear. Please practice, and definitely you can solve by your own, and this is the question which is going to answer in your question paper. Thank you so much for watching and staying till the end. If you really like, raise your thumb, pass it on to your friends, share it with as many friends as you can. That is the greatest help to this channel. Thank you so much.